All right, so let's talk about interference. Let me just give you an example of interference. Let me, I gotta pull a couple dudes off of here. Whoopsie daisy. Stuff likes to fall out on me. All right. Interference is basically when two waves, they interfere with each other, but I'm trying to find my, some of my stuff comes up missing here. All right, people, what you do with it? There we go. I found it. I grabbed that one. My wave stuff here. All right. Wave interference is basically when two waves across paths. Light can do that. Sound can do that. Have you ever listened to the radio and all of a sudden it cracks in? That's destructive interference. What it does is it messes up your signal. There is constructive interference that you can amplify a signal. So if you're trying to pick up a TV station that we used to have, my dad used to have an amplifier and hooked onto our TV antenna. This is before cable, before we poor people. All right, we had 3, 6, and 12 and PBS, and add the antenna outside. So my dad would hook up an amplifier. An amplifier would strengthen the signal, could make that signal a little bit stronger going through a TV. All right, so you're trying to pick up everything. So here's a wave. All right, going in all directions. She's not looking at me.
Yeah.
See that wave? All right. See what we got here? They're superimposed. But watch what happens when I just turn them a little bit. See the interference that's taking place? I kind of mess those up a little bit. I'll let you pass those around. That's an example of interference. When you have waves that are out of phase, that have different frequencies or different wavelengths. All right? Now, here's a case. Watch what happens. I'm going to have to bookmark this. Here's a wave. Here's a wave. Guess what happens? They begin interfering with each other. This can be a good thing. All right? Because if you're trying to pick up something that has a wave to it, let's try to get the same frequency. So this is let's make this 300. Watch what happens. This wave is 300. This wave is 300. What does it do? I'm gonna have to bookmark this.
Makes it bigger, faster.
Beats. Hold on. It amplifies it. All right? It amplifies it. All right? But what if let's deal with the interference. That's 250. All right. My case was and I don't think, see, my last applet has been dissolved, so I've got to do this. But what happens if I shift one of those waves a half a wavelength over?
Oh,
What's going to happen?
they wouldn't meet up.
Let's see. I'm screwing this up here. So if I superimpose, what's this added together? What do you end up getting? A flat line. They destroy each other. They kill each other. All right? So there are cases, now let me say this. Constructive interference can be good for us. Destructive can be good for us. You might think, wow. Well, they actually have headphones that like if you work in a factory, that can actually capture the frequency. Like if you're in a factory and they're what happens is the headphones capture that frequency and mixes with it the same frequency, but half a wavelength over. What does that do to the sound? Kills the sound. So, and now my daughter tells me that she's got, oh my gosh, these are what, $200 headphones. I thought $20 headphones was sufficient for me. But she's got these $200 headphones. And what ends up happening is, did I turn this on even? I did, all right. And what they do is they're noise canceling. Anybody have those in here? You have those? How much you pay for yours?
Christmas present.
You don't know how much?
Under 200, I think.
Okay. And do you hear outside noise?
Very little.
Because what it does is it takes that outside noise and cancels it out, and then you get the crisp, clear headphone stuff. By the way, we need to talk. I got that email, and I want to send it to your email. I'm going to send it to Ms. Shackles, and then give me your emails, and I'll send it to you, and we can talk on that. And you'll have to talk to Miss, because I have no clue what this protein stuff means, okay? I'm out of loop on that, right? So you can actually use destructive interference can be a good thing. It can also be a bad thing. You know, it's kind of like you're listening to a radio station. AM radio is really, 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 really susceptible to that. You know what I'm talking about? You ever listen to AM radio and you hear lightning? Even FM can mess it up. But think about this: EM waves, interference can be a bad thing. Sound. There can be constructive and destructive. You know, if what happens if you have two? I'm not in chorus. Anybody in chorus here? All right. So if you're saying ooh, and then you have another person ooh, and you're at the same frequency, what happens? It gets what? Louder. You get 3 people louder, 4 people louder. All right. So I don't know much about music, but like I said, that's the best I can do as far as singing. All right. Questions at this point, because I'm really tying up some things. Are we cool on constructive and destructive? Are we good? We understand the interference thing, right? Are we cool? Alrighty. So let's go on, get some definitions here. Let me go on here to. All right. So I bookmarked that. So let's go back to our phone here. All right. Things you need to know here. Let's go back. We talked about the 3 types of main waves, and we have what? There are 2 types. There's a transverse wave and longitudinal. Transverse waves are more along the line of either mechanical waves, like a guitar string vibrating, or a light wave. And longitudinal more in line with what? Sound, right? So, look at that, they pulled the old phone in here. Frequency is a number of cycles per second. Looking through here. Now, the speed of sound. I want you to get this down. 331. What formula do I have? I don't know if I've modified that since. All right. 331. If you want to know the velocity of sound, is dependent upon what the temperature is outside. So 331.5 plus 0.6 T. Now the 0.5 is always in question. Actually, I'm going to pull it off. I used to always put 0.5. I think they've honed that and refined that. All right. I don't think this is in your book. Pretty confident. The speed of sound changes with whatever the temperature is. So if it's 0 degrees outside, and this is not in Kelvin, this is 0. What's the speed? Oh, that's going to be meters per second. So let me just put that up there. Meters per second.
So the temperature in this is in Celsius?
What's that?
Is this in Celsius or is this in...
That is in Celsius, yes. All right. Y'all with me here? Makes sense? Sometimes my stuff starts coming apart. All right, so I'm gonna have Scotty to do something for me. I'm gonna have him to tape the positive and the negative on here just a little bit, but don't do it yet here, because you're gonna help me put that together. A lozenge? You want a lozenge?
Good.
All right. So sound is 331 meters per second plus 0.6 T. All right, that's air. That's in air. Everybody catching that? So if it is 0 degrees outside, speed of sound is 331. So you tell me, you work this for me. If it's 20 degrees, 20 degrees is around 70, a little bit above 70 degrees Fahrenheit. So if it's 70 Fahrenheit or 20 degrees Celsius, what is the speed of sound at 20 degrees Celsius?
343.
What is it?
343.
343. And that's what you'll get, because a lot of times they'll say it's like standard temperature or standard day, 343. If they ever say, if they don't give you what the speed of sound is, just assume 343. But this is speed of sound, and this is why, we're going to talk a little bit later, why your instruments sound different, especially your flutes and the long instruments, stuff like that. We're going to see the idea behind that. But let's go to this. Air, 331 at 20 degrees at 343. You just figured that, right? Carbon dioxide. Now look. Look what happens when you got, those are gases. What happens when you go to solids? In other words, more dense material. What happens to the speed of sound? Did everybody get 343, by the way? Huh? Okay. It does what? It increases, right? Think about this. Speed of sound in air is 343, but in steel it's 5,960. Water, yeah. Seawater is 1,500. They always say that, like, you have to understand, sound travels 5 times faster in water. This is why some animals, and it's actually a good medium, all right, for travel sound. This is why they say sharks, if you're flopping in the water, a shark can sense a wounded creature in the water several miles away. And then it goes and then it snaps and eats it. All right. You okay with that? All right. As kids, don't do this, okay? Steel. Somebody take the steel and do steel 5960 and divide it by the speed of sound in air. So 5960 divided by 331. Tell me what you get, how many times? 18 times. So sound is 18 times faster in steel than in air. And we used to do this as a kid, when we didn't have video games and cable TV and all that other crap. We'd go do fun things. We'd go hang out the railroad track, wait for the trains to come and play on the track, okay? So we put our ears to the track, because what we would do is, when that track, went for miles and curved, you couldn't see the train. But what you would do is put your ear to the track, and you could hear the train coming. Even though you look both ways, you put your ear to the track. We also put pennies on the track too, It was something I even taught my daughters. Hey girls, let's go put pennies on. Yeah! So we went to put pennies on. Anybody ever do that? Put pennies on a railroad track? You did? Oh, good, somebody. Now, you always put 10 on there. You're lucky to retrieve 2 or 3. So we always put a bunch on there, and you're lucky to find, like I said, if we put at least, my daughters and I think we put like 10 on there. We retrieved 2 or 3 really mashed out. We taped one time because the train ran over. It was like that. It was flattened out, and so they always tell you, don't do that, because you know what? A penny, you can cause a train to derail. No, you can't. It ain't gonna happen. All right. They just don't want you playing near the track because they lied to you. All right. So we'd put our ear up to the track and we could hear. And what would happen? A few minutes later, here's the train coming, and you get away from the track. You don't have your ear on the track when the train's coming. Right? That's just not a cool thing to do. But it was a common thing. And like I said, sound travels faster. So think about this. Sound requires a medium. You guys got to get this. Sound requires a medium. Air is a good medium. Water's even better. Steel is even better than that. But what happens? We talked about this yesterday. I'm more of like I said, a Star Trek fan. You okay? You starting to?
Yeah.
You getting tired on me here?
A little bit.
Okay, that's cool. You know, you're watching Star Wars, Star Trek. We talked about the Enterprise attacks. We talked about this yesterday, right? Did we talk about this yesterday? So the Klingons attack, and the Federation ship shoots and blows up a Klingon ship, and what happens? You hear the sound. And the problem is out in space there is a vacuum out in space. You can't hear anything out in space. There's no sound because sound requires a what? A medium. So if I basically, on this wall right here, and I took away just a fraction, let's say between you and I removed a half inch of air between me and you. All right? If I did a snap of finger, you wouldn't hear me anymore. That's what I said. Because as soon as what happens when I talk, it does what? It vibrates those molecules. Vibrates, and goes into your ear, right? Well, what happens when I vibrate those molecules and it comes to a vacuum? They stop vibrating. Yeah, because there's gazillion, I don't think that's the number, gazillion, billion, trillion molecules here. And what's really interesting, how your throat, really amazing, your throat, you talk, it vibrates those molecules, right frequency, right loudness, but your ear is also super, super duper sensitive to be able to pick up. It is amazing how sensitive your ears are able to pick up that information. All right, so what we're going to do, I want you to try, please, could you tape those on there, those electrodes? Let's get some noise going here. All right, so let's tape them onto the battery. Tell me when you're ready. All right, and while he's still working on that, see if we can get this in the near future here. All right, if you go to, hey! Oh, always a pleasure having you in class. Who are we looking for, pal?
I'm looking for my son. He's not in this one.
Oh, no, next hour.
He's in third hour.
Next hour.
I feel we have second hour.
Yeah, who knows? All right. I want you to go, I guess these are not in the PowerPoint. Infrasonic, I guess he's still working, is less than 20 hertz. Ultrasonic is greater than 20 kilohertz or 20,000 hertz.
It wasn't making a noise when I touched the red one.
Are you sure? There you go.
This one.
Tape it on
That
there.
one needs to be farther over.
You just tape it, do whatever you do. Just when we get it taped on there, because we need this continuous sound, because I'm going to put it in a vacuum. All right, infrasonic, this, and by the way, in between, here's the deal. The audible range. The audible range. And this is in hertz. All right. Is he still working on it? Okay, is it taped on? Do you need help? Do you want the girls to help you?
The black wire is being troublesome.
Just get it on there and tape it. Tape it on there.
Here, you want to grab the tape? This one has to be at a weird angle.
Okay, so what am I doing?
You need tape.
Actually, if it'll stay going that way, here, let me see it.
No, because the black wire moves around and it cuts off. See, the black wire has to be like up for some reason.
Oh, and maybe, well, wonder if it's,
Yeah, I guess it works.
no, I think what it is, it's got glue on it, is maybe what it is. Let me clean that off a little bit.
Red wire is attached.
Okay, now let's get her to. Try it now, pal. You know what I could try? Let's try something different. You may punch me on this one. I'll bet you this will work better. Tell me if, we'll try, we gotta get a sound device going here in just a little bit. I think this might work. Let's hope this works. Let me see the battery here.
You want me to take off the...
Yeah, go ahead. Let's see if this will work. Oh, there we go. That worked. All right, let's just go ahead and stick this on here. Annoying.
One of the girls told me that one comes over, can't figure it out.
This is a vacuum.
Yeah, I can hear it barely.
Still hear it.
Well, then call you.
All right, hold on. I'm trying to-
No one's gonna get the video.
I
All right. Now listen.
The video for Kylie.
Oh, I can't.
Still hear the sound?
No,
Barely.
it's not at all.
All we're gonna hear is a bump.
See, you don't hear the sound anymore, do you? Hold on. Hold on, I'll shut the pump off here in a minute. All right. Hear anything? What we've done is we've removed all the air. You might even hear something mild because it could be vibrating this thing. Nothing? I've got to get this off or I'll have oil in this. Anything? You didn't hear it before, did you? I actually could hear it when I got real close, but it was the vibration of this thing. Let's turn it off now. All right. Makes sense? Pretty cool? We removed, I just showed you that if we remove all the air, sound is going to cease. Because sound requires a medium. And our medium is, our current medium is, we use air molecules since we're not really like in water and live underwater. That's not how we communicate, all right? So, the audible range is 20 to 20,000 hertz. That's what we hear, approximately. Now, let's kind of go back to this. Outside of that range, ultrasonic is greater than 20,000 under 20, and we always call that the audible range. That's in general. That is somebody has super duper duper good hearing, young, and everything like that. Is going to be close, but that's just the average. Let me.
Where's supersonic fit into this?
Supersonic is faster than the speed of sound. Supersonic. We're going to talk about that a little bit
Faster
later.
than
Mach
300
speed.
Faster
Sup-
than 331 meters per
Yes, yes. And we call that Mach speed. Mach 1 is 343. Mach 2 is 2 times. Our jets, I think, are Mach 3 at this point.
How many hertz would that be?
Well, now that's different. Speed of sound and frequency.
Okay.
These are frequencies.
Okay.
These are frequencies. And I'm going to try to find sound. Okay, so I'm going with you here. Let's go back to what we did
The
before.
fastest plane of all time was launched from another plane.
All right. On the average person,
I just know it was a rocket.
they say that average person, all right, I'm playing 23,000 hertz. 21, 20. I'm around 20,000 hertz. They say that's around that's the most extreme audible range. Taking her down, I'm at 19,000 hertz. 17,000. 16,000? Are you getting it
Well,
now?
I could hear that 17.
Oh, 7.
All right, 15. See, I can't hear that. I can begin to hear that. That's 15,000 hertz. Maybe I didn't hear that. Oh, 11,000. Now I'm starting to hear it really clear. 11,000, 10,000, 9,000, 8,000, 4, 3, 2, All right, let's see how I can raise this up.
So you're saying that if you play two of those together, they would cancel each other out?
Well, no, you'd have to have them
At the same-
off beat here, off
Can we get
out of
two together?
phase. This is 100 hertz, but I'm not hearing it.
Sounds like the
I can hear this, but I have to do that. That's 137.
slide whistle. That's what it sounds like.
Like a cat when it's-
Yeah. All right. This is the app called Sonic. It just says Sonic on it. All right. So basically, you can try the different frequencies. So they had the mosquito ringtone out. Kids would do, and so the mosquito. Does anybody hear that? I don't know if it is. It says it's playing. I don't know if anybody can hear that. Well, there was a ringtone that older adults. So what kids used to do is have the mosquito ringtone on their phone, so when their phone went off, they could hear it, but the teacher could not. I couldn't hear it, you know. So what I did for fun during detention one time, I had that down. I had a BlackBerry at that time, and I just felt to annoy the people that were in there. I'm working on my computer, my pinky. I pressed the play button. It would play for like 10 seconds. You got a couple kids, start looking around. This is me. Pinky, I hit it again, hit play again for 10 seconds. Everybody's looking around. Why are you looking around? Oh, nothing. Hit my pinky, hit play again. Who's doing that? Hey, why are you talking during detention? Well, somebody, I hear something, sound going off. I was like, I don't hear anything. Be quiet, or I'll write you up. Hit the play again. I annoyed them all. So I did this during detention. Now, at the end, I did tell them that was me doing that. But I would hit the play. I couldn't hear it. They could hear it. All right, they could hear it. So but I could not hear. I could not hear that frequency. All right, let's move right along here. So we understand speed of sound, infrasonic, ultrasonic. Now, supersonic has to do with speed of sound. These are frequencies of sound. So these are measurements of sound. Think about sound. There's frequency, all right, loudness, but also speed. And the speed of sound, if you try, if you go supersonic, that just means you're going faster than the speed of sound. All right, Mach 1 is 1 times the speed of sound. All right, Mach 2, Mach 3. We're up about Mach 3, but supersonic just means faster than the speed of sound. All right, are we cool on this? Are we good? All right, I'm going to finish off with this lightning. Did this when I was back. I used to do this with lightning. Lightning, okay, I want you to think about this. Light travels almost instantaneously here on Earth when we see something on Earth. How come you can see me? If I wave at you, you can see me because what? Light is reflecting off of me onto you, and you see it. Agreed? You can see me, all right? However, if I turn my flashlight on, it's almost instantaneously. When I wave at you, you see it almost instantaneous. Have you ever gone to a firework display or watching lightning? You'll see the lightning, and then boom. Or you go to a fireworks display, you see the light. 1, 1,000, 2, 1,000, boom. All right. The general rule is this. If the light that I see from the firework is just about what? How fast?
3 times 10 feet.
Meters per second, but kind of in non-numeric terms.
Very, very fast.
Very fast. Almost instantaneous, right? So when I see the firework display or lightning, it's instantaneous, right? The sound takes a little while longer. Well, sound travels at 343 on a typical warm night, 343 meters per second. How many feet are in a meter? Approximately 3 feet. 3 times 343 is approximately, rounded to the nearest 1,000 feet. 343 times 3 is what? about 1,000 feet. So that means sound is traveling around 8,000 feet per second. So I'm out there, I'm relaxing in my backyard watching a storm brew, and here's what I see. I see the flash. What do? Once you see the flash, start counting. 1, 1,000, 2, 1,000, 3, 1,000, 4, 1,000, 5, 1,000, boom! How far away was the lightning strike? About 5,000 feet. And remember, there's 5,280 feet, so about a mile away. You look out there, all of a sudden you see a flash. You're like, you see the flash. 1, 1,000, boom! What does that mean?
Right on top of you.
That thing, huh?
It's either almost on top of you.
It's
or
right
almost on
close
top.
to you. You see the flash, boom, it's really close to you. Make sense? So do that sometime. So the general rule is every 1,000, it's 1,000 feet. And then where it comes from is 343 meters per second, which is approximately 1,000 feet per second. And just count. When you see lightning strike, start counting. 1, 1,000, 2, 1,000, 3, 1,000, 4, 1,000. Start doing that. Make sense? All right. Questions. Questions. All right. I'm going to give you, let me write this down here. Because I've already given you the one set. I'm stopping around 0.5. Oh, that was a good lead. Hold on.
30,000.
Why?
Doggone it. There we go. All right, so that was up to 0.6. We'll be starting 0.7 tomorrow. All right. My pencil's not working very good. All right, so 16.5 to 0.6. I'll be giving you a handout tomorrow. So I gave you up to what? What was the last one I gave you tomorrow?
27.
Up to what?
27.
All right. 31, 32. $39 and $41. All right, let me see this. 31, 32, 39, and 41. And I gave you up to what yesterday?
27.
Up to 27. All right. Did I, let's see here. On number 17, let me give you a hint on that one. The tension in each rope on 17 is 13 newtons. On 17B, see there, the tension in the rope across that whole rope is 26 newtons. But on B, the tension in each rope is 13 newtons. That's on B, okay? So go ahead and work. You'll be getting another assignment tomorrow, then all period to work on Thursday, okay? So let's go ahead and get after it.
Did you get it done? Your homework? I did the laptop. Oh. I do give
Oh, camera. Do you want me to put it?
Oh, thank you, bud.
Do you want me to hit the camera?
Oh, yeah, please.